Somewhere inside the idea of a generation ship, there is a point where the word spacecraft begins to feel too small. A spacecraft is usually built around a journey. It leaves one place, crosses a distance, and arrives somewhere else while the people aboard remain part of the same mission. A generation ship would belong to a different category. It is still hypothetical. No one has built one, and no existing design has solved all of the biological, engineering, and social problems involved. But the defining idea is simple enough. The voyage lasts long enough that more than one human generation must live aboard. That changes almost every question. The people who design the ship may never see its destination. Some of the people who eventually arrive may be born after Earth has become a memory, carried in recordings, maps, stories, and inherited knowledge. For them, the vessel would not feel like transportation in the ordinary sense. It would be the place where water comes from, where food grows, where gravity is created, where machines are repaired, where children learn, and where the night sky moves outside a wall they cannot simply open. So the engineering problem is not only how to keep a machine operating for a very long time, it is how to build a place that can remain understandable, repairable, and livable after the people who first assembled it are gone. That means ordinary failures matter as much as dramatic ones. A pump that wears out after 20 years, a sensor that slowly loses accuracy, a crop system that needs rebuilding, or a section of shielding that has to be replaced, may never become a crisis if the ship was designed for repair. The real measure of success would be whether such work can become routine, repeated by people who were not alive when the original drawings were made. We already know how demanding a much smaller closed habitat can be. On the International Space Station, environmental control systems recover water, manage cabin air, remove carbon dioxide, and help maintain conditions that allow a small crew to live and work in orbit. NASA has demonstrated water recovery approaching 98% on the station. That is a major achievement, but the station still depends on resupply, ground support, replacement hardware, and a planet only a few hours away by spacecraft. A generation ship would have to carry the logic of self-reliance much farther, and even the floor beneath your feet would become an engineering decision. One possible approach is rotation. A habitat can spin so that its structure continually pushes inward on the people standing along its outer interior surface, creating an effect that can resemble gravity. The relationship between rotation rate and radius is well understood, but the human response to long-term rotation is less completely settled. Larger radii can allow lower rotation rates for the same apparent gravity, which is one reason serious studies of rotating habitats often become very large. Size then would not be there only to make room for more people. It could emerge from the needs of bodies, farms, shielding, machinery, storage, repair routes, and systems that must continue working through failures no one can schedule in advance. The transcript that inspired this episode begins from the problem of building a city-sized spacecraft. Here, we will follow a different path. We will begin inside the moving world itself, with the ordinary conditions that have to exist every morning, every year, and eventually every lifetime. Because if a ship must carry generations, the deepest question is not whether it can cross the distance between stars. It is whether it can remain a world while it does. Before any world can move between stars, it has to decide what down means. On Earth, that decision is made for you. Gravity pulls your body toward the ground. Water settles into containers. Warm air rises. Loose objects fall. And every room is built around the expectation that one direction will always be below. Inside a large spacecraft, none of that is automatic. A ship could simply coast in weightlessness, but a voyage lasting generations would make that choice. A biological experiment on a scale no one has ever performed. Human spaceflight has shown that long periods without normal loading affect bone, muscle, fluid distribution, balance, vision, and other systems. Exercise can reduce some of those effects, but it does not recreate the full mechanical environment of living under gravity. For a population expected to grow up, age, work, recover from illness, and perhaps carry pregnancies over many decades, engineers would have strong reasons to consider a more persistent gravitational environment. The most familiar method does not require a new force. It uses rotation. Imagine standing inside a large wheel, turning in space. Your body naturally wants to continue moving in a straight line. The curved floor keeps redirecting that motion toward the center. What you feel through your feet is the floor pushing against you. If the wheel is large enough and turns at the right rate, that steady contact can provide something that feels much like weight. The physics is simple enough to write on a classroom board. The experience of living inside it is not. In a small rotating habitat, the floor has to move through its circle more quickly if you want stronger, apparent gravity. That means your body changes direction more often. Your head and your feet also travel along circles of different sizes. When you turn your head, bend down, climb a ladder, or move toward the axis, your inner ear encounters motions that do not occur in an ordinary building on Earth. Studies of artificial gravity have long treated rotation rate, radius, gravity gradients, and motion sickness as connected human factors problems rather than separate engineering details. One way to make the experience easier is to make the habitat larger. With a greater radius, the spinning surface can produce a given level of apparent gravity while rotating more slowly. NASA-supported concept work that rotation rates of only a few revolutions per minute can become uncomfortable for some people, and that creating near-Earth gravity at roughly 1 or 2 revolutions per minute pushes a habitat toward kilometer-scale dimensions. That does not establish one required size for a future generation ship, because tolerance varies and the acceptable gravity level is still an open design question. It does reveal an important direction. Human comfort can make the machine physically larger, and once the radius grows, the rest of the world grows with it. The pressure shell covers more area. Structural members become longer. Air fills a greater volume. Electrical lines, water pipes, communication networks, maintenance corridors, farms, workshops, and emergency routes spread farther from one another. A larger habitat may allow a slower rotation rate, but it also asks the civilization aboard to maintain a larger piece of architecture. Rotation adds another kind of structure as well. A spinning habitat carries angular momentum, so docks, engines, observatories, and industrial sections may not all want to share the same motion. Some designs separate rotating living areas from non-rotating hubs. Others imagine paired or counter-rotating masses so that the larger vehicle can manage the effects of rotation more gracefully. None of these arrangements is mandatory. They simply show how quickly one decision about human bodies reaches outward into bearings, joints, control systems, cargo routes, and the overall shape of the ship. Even the transition between rotating and non-rotating regions becomes part of daily architecture. A person moving toward the hub would feel apparent weight decrease as the radius shrinks. Cargo handling could exploit that difference, while elevators, spokes, and transfer corridors would need to manage it safely. The ship's map would contain not only places, but changing gravity. This is where the idea of a generation ship begins to separate from the image of a crowded vessel. If people are going to spend entire lives inside, the geometry can provide more than gravity. It can provide distance. Farms can be separated from machine shops. Sleeping areas can be placed away from noisy industrial systems. Hospitals can have protected zones. Children can grow up with routes that take longer than a few seconds to cross. a neighborhood can become a real neighborhood rather than a row of compartments sharing the same vibration through the walls. None of this means a future ship would need green fields beneath an artificial blue sky. Those familiar paintings are design explorations, not forecasts. A real vessel might use several rotating rings, multiple connected habitats, counter-rotating sections, or arrangements we have not yet tested. Some sections might rotate while docks, observatories, engines, and manufacturing areas remain relatively free of rotation. NASA has examined concepts that separate artificial gravity habitation from other spacecraft functions, which leaves many possible architectures open. But every solution has to answer the same bodily question. What does a normal day feel like? A person wakes and stands up. A cup stays on a table. Water runs toward a drain. A child learns to walk without needing to relearn the direction of the floor every few meters. A technician carries a tool case through a corridor while the ship continues its turning motion around the axis. For someone born aboard, the rotation would not feel like a clever engineering trick. It would be part of the background conditions of life, as unremarkable as the weight of a blanket or the way rain moves down a window on Earth. There is a useful inversion here. We often imagine that the ship must become enormous because it carries a large population. But the population is only one reason. The ship may become enormous because bodies prefer certain motions, because machinery needs separation, because farms need area, because failures need alternative routes, and because a permanent home asks for spaces that are not all doing the same job. The walls move outward until the vehicle begins to contain geography, and once a ship contains geography, another problem appears. Every square meter of that larger world has to be protected from an environment that does not care whether the space behind the wall is a machine room, a garden, or someone's bedroom. A moving world needs walls, but not walls in the ordinary sense. On Earth, a wall separates one room from another, holds up part of a roof, keeps out rain, or carries the weight of floors above it. Around a generation ship, the outer structure would have to do something more complicated. It would need to hold atmosphere inside while surviving an environment where there is almost nothing outside to slow an incoming particle before it arrives. Space is not empty enough to ignore. Tiny grains of natural material move through the solar system. Human activity adds debris in some regions, near Earth farther away. The artificial debris becomes less important, but natural particles remain. Most are very small. That does not make them harmless. At high relative speed, even a small object can release enough energy during an impact to damage exposed hardware. The usual solution is not simply to make one wall thicker. Spacecraft already use layered protection against small, high-speed particles. An outer bumper is placed some distance ahead of the pressure wall. When a particle strikes that first layer, the impact can break it apart, melt portions of it, or spread its material into a wider cloud. The empty distance behind the bumper allows that cloud to expand before it reaches the next barrier. The protection comes partly from material and partly from geometry. A generation ship could extend that principle into an entire architecture. Instead of one polished shell surrounding the habitat, there might be several regions between inhabited rooms and open space. Some layers would be structural. Others could carry insulation, pipes, in storage, sensors, or replaceable shielding panels. Certain sections might be designed with the expectation that they would accumulate damage over decades and eventually need repair. That expectation changes the meaning of a hull. A hull is no longer something that must remain untouched for the entire voyage. It becomes something the population maintains. Outer panels could be inspected by cameras or robotic systems. Sensors buried within the structure could watch for pressure changes, vibration, or damage. Some sections might be replaced during scheduled maintenance rather than after an emergency. A crew living aboard for generations would learn the condition of its outer defenses in much the same way a coastal town learns the condition of bridges, seawalls, and water lines. Parts age. They are measured, they are serviced, and the world continues. Impacts, however, are only one reason to place mass between people and space. Radiation presents a different problem because it does not usually announce itself with a visible hole. Beyond the protection provided by Earth's atmosphere and magnetic environment, astronauts can be exposed to energetic particles from the Sun and to galactic cosmic rays arriving from far beyond the solar system. These forms of radiation are not identical, and they do not interact with shielding in identical ways. A burst of energetic solar particles can arrive during an active solar event. Depending on the ship's location and the nature of the event, the population might benefit from temporarily moving into a more heavily protected region. Galactic cosmic rays create a more persistent challenge. They include atomic nuclei, traveling at very high energies. Some can pass deeply through material when energetic particles collide with shielding. Those collisions can also create secondary particles. That means radiation protection is not a simple matter of placing the densest possible wall around the crew. Material composition matters. Thickness matters. Arrangement matters. And no practical wall makes the environment disappear completely. For a ship designed to operate for lifetimes, shielding would become part of the interior map. Water is one obvious example of useful mass that could also contribute to protection. A large population already needs water for drinking, hygiene, agriculture, processing, and reserves. If some storage tanks are arranged around occupied regions, the water can perform two functions at once. Food stores, certain plastics, equipment, and other hydrogen-rich materials could also become part of the protective layout. The ship begins to resemble a system of nested spaces. Near the outside are layers expected to face the environment first. Deeper inside are machinery, storage, and support systems. Living areas can occupy more protected zones. Within those zones, smaller shelters can provide additional shielding when solar conditions make temporary refuge useful. A bedroom might be protected differently from a cargo dock. A nursery might be placed differently from a machine shop. A medical area might sit farther inside than a greenhouse window or an external observation bay. This is where radiation becomes architecture rather than simply a health calculation. Every decision about where mass is stored changes the protection somewhere else, and stored mass does not always remain stored. Water moves through the habitat, food is consumed, waste accumulates and is processed. Spare parts leave shelves and enter machines. Raw materials become finished components. If those materials also serve as shielding, the distribution of protection can change over time. So the ship would need to think about mass almost as a city thinks about traffic. Not every kilogram stays where it began. A tank can be drained. A warehouse can empty. A damaged component can move into a repair bay. A harvest can shift material from growing areas into kitchens, storage, people, and waste processing systems. The protective design would have to survive those ordinary movements. Some shielding might therefore be permanent and dedicated. Other protection could be built around materials that already have another purpose. The balance would depend on the mission, propulsion system, destination, acceptable risk, and whatever future research teaches about long-term human exposure beyond Earth. There is no single wall thickness that solves every generation ship. That uncertainty is important. A vessel moving through interstellar space would not face the same environment as a station in low Earth orbit. A fast ship could encounter small particles at relative velocities far beyond those experienced by many spacecraft today. A slower concept would face a different impact problem. The radiation environment would also change. As the ship moved away, from the sun, and eventually beyond the region dominated by the solar wind. The final design would depend on a journey no human vehicle has ever made. But the basic burden is already visible. Protection takes mass. Protection takes depth. Protection takes access. And protection takes maintenance. That last requirement may shape the vessel more than any artist's exterior rendering suggests. Imagine a service route running between two layers of the outer structure. It is not a place passengers visit. It may be narrow, unfinished, and filled with cables, sensors, attachment points, and removable panels. A technician enters because an impact monitor has reported something unusual. Nothing dramatic has happened. The atmosphere is stable. The inner wall is intact. A robotic camera has simply found a damaged section farther outside. The technician checks the readings, compares them with older inspections, and decides whether the panel can remain in place until the next maintenance cycle. Perhaps a small robot performs the replacement. Perhaps a human crew works from a protected service chamber. Perhaps future materials allow damaged sections to be repaired in ways we cannot yet use. Whatever the method, the important thing is that the ship was built with repair in mind. This kind of design changes the emotional scale of the voyage. The people aboard are not sealed inside a flawless object sent into space by distant ancestors. They inherit a structure that expects their participation. Someone teaches them how the walls work. Someone keeps records of old impacts. Someone understands which water tanks must remain full around a protected shelter. Someone knows how to replace a sensor hidden behind a panel installed before their grandparents were born. Knowledge itself becomes part of the shielding. Without maintenance, procedures, drawings, tools, training, and people capable of using them, layers of material are only temporary protection. A moving world survives because its inhabitants continue to understand the world they inherited, and behind those protective layers, another system works without stopping. Air moves through ducts. Water passes through filters. Carbon moves from breath into machines, plants, stores, and back again. Every meal begins another cycle. Every shower enters another loop. Every person depends on material that must be recovered, cleaned, separated, and used again. The walls can keep space outside. The next challenge is keeping almost everything else inside. Keeping almost everything inside sounds simple until you begin following individual atoms. A person drinks a glass of water. Hours later, some of that water has become moisture in the air. Some has left the body as waste, and some remains inside cells and tissues. A plant takes water through its roots and releases part of it through its leaves. Cooking sends more into the air. Washing moves it into drains. Every ordinary activity sends the same material into a different part of the habitat. On Earth, the larger environment quietly completes these cycles for us. Water evaporates, forms clouds, falls as rain, moves through soil and rivers, enters living things, and returns again. Oxygen moves through forests, oceans, animals, microbes, and the atmosphere. Carbon passes through food, soil, plants, air, and rock. Human cities participate in these cycles without having to contain all of them. A generation ship would have no river beyond its walls and no atmosphere extending over a continent. Its cycles would have to fit inside the machine. The International Space Station already provides a small example of what this means. Its environmental control and life support systems manage functions that include water recovery, air revitalization, and oxygen generation. NASA has also demonstrated water recovery approaching 98% aboard the station, reclaiming water that would otherwise have to be replaced by new supplies from Earth. For an orbital laboratory supported by regular cargo traffic, that level of recycling is deeply useful. For a world traveling for generations, the meaning changes. Suppose a system returns nearly all of the water passing through it. The fraction that escapes may be very small, but the voyage gives that small fraction time to matter. A loss that can be covered by occasional deliveries near Earth becomes a continuing subtraction when no delivery is coming, and the problem is larger than water. Oxygen must remain available in the right concentration. Carbon dioxide must be removed from occupied spaces. Trace contaminants have to be controlled. Nitrogen and other atmospheric gases have to stay within useful ranges. Nutrients used by crops must be recovered where possible. Metals, plastics, fabrics, cleaning chemicals, medicines, electronics, and countless minor materials all enter their own cycles of use, degradation, recovery, and replacement. A closed world is not one loop. It is thousands of loops crossing one another. That distinction matters because a loop can be very efficient when examined alone. Imagine a water processor that performs beautifully. It recovers almost everything delivered to it and operates for years with little trouble. But it still needs electrical power. Its pumps contain moving parts. Its filters eventually change. Sensors must remain calibrated. Seals age. Pipes accumulate deposits. Cleaning procedures create their own waste. The machine that closes one material loop depends on several other loops remaining open enough to support it. Electricity has to reach the pump. Replacement material has to reach the filter. A technician needs tools. The tools themselves have to remain usable. If a replacement component is manufactured aboard, then the manufacturing system needs feedstock, energy, software, cutting surfaces, lubricants, and its own replacement parts. Maintenance begins to reproduce itself. A generation ship would therefore need something more sophisticated than efficient recycling. It would need a material economy. Objects would move through stages. A component begins as usable hardware. It spends years inside a machine. Eventually it becomes worn hardware. Perhaps it can be repaired. Perhaps it is dismantled and its useful pieces sorted. Metals might return to manufacturing stock. Polymers might be reprocessed where practical. Parts that cannot be recovered may become stored waste, shielding mass, chemical feedstock, or material awaiting a technology capable of using them later. The distinction between garbage and inventory could become surprisingly narrow. A broken panel on Earth is easy to discard because the larger economy can produce another one. Aboard a distant ship, the atoms in that panel may still be valuable. Even after the panel has lost its original purpose, someone may remove the fasteners. Someone may separate the wiring. A machine may cut the remaining material into standardized stock. Years later, part of that same material could become a bracket in a greenhouse, a housing around a pump, or a patch inside a service corridor. Nothing about that process would feel futuristic to the people doing it. It would be maintenance. Food introduces an even richer cycle. Stored meals can support crews for a limited time, but carrying centuries of prepared food would create an enormous mass and storage problem. A multi-generational population would almost certainly require some form of food production aboard, although the exact balance between agriculture, stored reserves, and future food technologies remains uncertain. Plants are attractive because they can do several jobs at once. They can produce edible material. Through photosynthesis, they can use carbon dioxide and release oxygen. They move water through their tissues and into the surrounding air, where that moisture can be recovered. NASA has studied crop systems for long-duration exploration precisely because biological systems may eventually complement mechanical life support while providing fresh food. But a field inside a spacecraft is not simply a piece of Earth carried upward. Every part of agriculture becomes engineered. Light has to reach leaves at useful intensities and wavelengths. Water must reach roots. Nutrients have to remain available in forms plants can absorb. Temperature and humidity must stay within workable ranges. Pollination may need human or mechanical assistance for some crops. Diseases and pests cannot be allowed to move unnoticed through a food system on which an entire population depends. Even soil is optional. Some systems could grow plants hydroponically or with other controlled methods. Others might use engineered substrates. The right approach would depend on reliability, crop type, available materials, energy use, and the difficulty of maintaining the system across decades. Whatever the method, agriculture would become infrastructure. The farm would have pumps. The farm would have sensors. The farm would have replacement lights or optical systems. It would have plumbing, nutrient storage, harvest equipment, seed banks, cleaning procedures, and areas where one crop could be isolated from another if something went wrong. And because biology does not follow a maintenance manual with perfect obedience, the ship would need reserve capacity. A mechanical pump may fail according to wear. A crop can fail because of several conditions arriving together. A disease might spread. A nutrient imbalance might appear gradually. A seed line could perform differently after generations of cultivation. A growth chamber might remain mechanically healthy, while the organisms inside it respond poorly to some unnoticed environmental change. A population that depends on agriculture cannot assume that every harvest will be ideal. So stored food remains valuable even in a ship with extensive farms. So do multiple crop varieties. So does genetic diversity. So does having more growing capacity than the average year requires. Redundancy begins to look less like duplication and more like breathing room. There would also be people whose work is devoted to understanding these systems. Perhaps a child born aboard becomes interested in plants because one growing chamber sits beside the path to school. She learns the names of crops first, then the chemistry of nutrient solutions, then the behavior of microorganisms around roots. Decades later, she may be one of the people responsible for keeping the food system stable. Her knowledge would not be imported from Earth each morning. It would belong to the ship. That is one of the quieter consequences of a voyage longer than a career. Technical knowledge must survive generational transfer. A machine can be designed to operate for many years, but people still need to understand why it was designed that way. Procedures can be stored in databases, yet procedures alone do not create judgment. Someone has to recognize when a sensor reading is believable and when the sensor itself may be failing. Someone has to know which unusual vibration can be watched until morning, and which one means a pump should be shut down now. The ship would need schools not merely because children need an education, but because the spacecraft requires successors. Every critical profession has to continue. Doctors, engineers, agricultural specialists, electricians, programmers, machinists, ecologists, people who understand atmosphere control, people who understand water chemistry, people who can teach all of those subjects to someone younger. The moving world carries not only spare parts but spare knowledge, and knowledge, like water, cannot simply be stored once and forgotten. It must circulate. Some of it becomes formal training, some passes through apprenticeship, some survives in diagrams, simulations, recorded failures, and old repair notes. Some may be transmitted through habits so ordinary that the people aboard barely notice they are maintaining a tradition. A technician checks a seal in a particular order because another technician taught her that sequence 30 years earlier. A farmer keeps two varieties of the same crop in separate growing areas because a disease event before his birth changed agricultural policy. A child learns never to move stored water from certain protected compartments without checking the radiation plan first. Daily life becomes intertwined with engineering memory. This is where the word ecosystem begins to become useful, though it must be used carefully. Earth's biosphere is immensely complicated and open to energy from the sun, while cycling material through oceans, atmosphere, soil, organisms, and geology. A generation ship would not reproduce Earth in miniature. It would create a constructed system with far fewer species, much less material, carefully managed energy flows, and boundaries defined by machinery. NASA research into bioregenerative life support explores how biological processes such as crop growth might work together with physical systems to recycle resources during deep space exploration. That research remains far removed from demonstrating a self-sufficient human ecosystem capable of operating for centuries. NASA science. The gap is important. We know how to recycle portions of a crew's water. We know how to regenerate oxygen aboard spacecraft. We know how to grow a range of plants in controlled environments, including experiments in space. What humanity has not demonstrated is a sealed technological habitat supporting a large population, extensive agriculture, manufacturing, medicine, waste recovery, and ecological stability, without external resupply across many human generations. A generation ship would have to cross that gap before it crossed interstellar distance. Perhaps its systems would never become perfectly closed. Perfection may not even be the useful target. Instead, designers could give the vessel large reserves of materials whose losses are difficult to eliminate. Water could be carried in quantities far above immediate daily requirements, serving simultaneously as reserve supply and shielding. Carbon, nitrogen, phosphorus metals, and other valuable elements could exist in stockpiles large enough to absorb imperfect recovery. The ship could begin its journey with warehouses intended not for the first crew, but for people a century later. Imagine opening such a storage area. The containers are labeled in systems designed for you were born. Some hold standardized metal stock. Others contain membranes, seals, fibers, catalysts, electronic components, medical precursors, nutrient compounds, or materials that the original planners judged too difficult to manufacture aboard. Nothing inside appears dramatic. There is no engine, no window, no view of the stars. Yet this may be one of the most important rooms in the entire vessel. It contains time. Every spare item is a future problem already partly solved. Every reserve kilogram gives later generations another option. And as the ship becomes better at repairing, recycling, and manufacturing, perhaps those reserves diminish more slowly than anyone expected. The population might even improve the systems it inherited. A life support loop, redesigned in the second generations, could recover material more effectively than the original version. A manufacturing process introduced decades into the voyage might turn what had once been useless residue into feedstock. Agricultural knowledge could become richer as generations of growers learn how particular crops behave in the ship's environment. The vessel would not need to remain technologically frozen at departure. It could become a civilization capable of maintaining and modifying its own machinery. That ability may be more important than making every original component last for centuries. No pump needs to survive the entire voyage if the population can replace pumps. No computer needs to remain operational forever if computing hardware can be repaired, remade, or substituted. No single greenhouse needs to be immortal if agriculture exists as a resilient network rather than one indispensable room. The problem shifts from building permanent objects to preserving permanent capabilities. The capability to purify water, the capability to maintain atmosphere, the capability to produce food, the capability to make tools, the capability to diagnose disease, the capability to replace damaged structure, the capability to teach the next person how to do all of it again. When those capabilities circulate successfully, the moving world begins to resemble something more durable than any individual machine inside it. It begins to resemble a society, and a society requires energy. Every pump moving water, every lamp above a crop, every processor cleaning air, every furnace reshaping metal, every computer tracking the ship's condition, and every inhabited room kept within a livable temperature depends on a continuing flow of power. Material can be recycled. Energy cannot be recycled in the same way. It must keep arriving from somewhere. For a world traveling farther and farther from its original sun, that question leads toward the systems buried deepest inside the ship, where the machinery of ordinary life meets the machinery that keeps the entire vessel alive. A world between stars would never truly sleep. Even while most of its population rested, pumps would continue moving water. Air would continue passing through filters. Computers would continue comparing thousands of sensor readings. Refrigeration systems would hold food at safe temperatures. Agricultural chambers would maintain their cycles of light and moisture. Somewhere in the structure, machinery would be removing heat that human bodies and electrical equipment had quietly released into the habitat. All of it would depend on energy arriving in the right place at the right time. Near-Earth solar power is an obvious resource. Sunlight is abundant enough that spacecraft and orbital stations can convert it directly into electricity with photovoltaic arrays. Closer to the sun, the available solar energy increases. Farther away, it falls rapidly with distance. An interstellar vessel eventually leaves that useful neighborhood behind. At twice Earth's distance from the sun, the same area receives only about 1/4 as much sunlight. At 10 times the distance, roughly 1/100th. Continue outward, and enormous solar collectors would be required to produce the power that much smaller arrays could provide near Earth. Each ship intended to cross the space between stars would therefore need an energy system that does not depend primarily on the sun it left behind. That requirement reaches into nearly every part of the design. The ship needs energy for life support before it needs energy for propulsion. It needs power for agriculture, manufacturing, computing, communications, medical equipment, lighting, transportation within the habitat, and the endless small machines that make ordinary life possible. Then there is heat. Every useful form of energy eventually leaves some heat behind. A lamp warms its surroundings. A motor warms its bearings and coils. A computer warms its processors. A person turns chemical energy from food into movement, thought, and body heat. A factory reshaping metal produces still more. On Earth, unwanted heat can move into air, water, soil, and weather systems. A city can release it through cooling towers, rivers, winds, and the atmosphere. A spacecraft has no surrounding air to carry heat away. In vacuum, the final route is radiation. Large surfaces must release thermal energy as infrared radiation into space. These radiators may not be the most visually striking parts of a generation ship, but their size could become one of the defining features of its exterior. Power systems and radiator systems would therefore grow together. Produce more energy, and more waste heat must eventually be rejected. Run larger farms under artificial lighting, and some of that electrical power becomes warmth. Expand industrial production and furnaces, motors, processors, and chemical systems. Add another thermal load. Even an extremely efficient machine cannot make this relationship disappear. Efficiency can reduce waste, it cannot remove thermodynamics. This produces a strange image. From inside, the ship may feel like a landscape of neighborhoods, gardens, workshops, schools, and passageways. From outside, much of its visible structure could belong to systems that inhabitants rarely think about. Radiators, power equipment, shielding, antennas, storage tanks, service trusses, and machinery whose only purpose is to keep the interior ordinary. The ordinary life is the achievement. A glass of cool water, a room at a comfortable temperature, a greenhouse that does not overheat when thousands of lamps are operating. a hospital that continues functioning when one power bus is taken offline for maintenance. Those conditions depend on an electrical system designed not merely for capacity, but for survival. A city on Earth is normally connected to a wider grid. If one generator stops, electricity may arrive from somewhere else. Fuel can be delivered. Damaged equipment can be replaced by factories in another region. The moving world cannot assume that kind of outside support. Its grid would need layers. Several sources of power could feed separate parts of the vessel. Energy storage could bridge short interruptions. Critical systems could have independent supplies. Sections of the grid might disconnect themselves after damage so that one electrical fault does not spread through the entire habitat. Hospitals, atmosphere control, water circulation, and navigation would not compete with optional loads in the same way during an emergency. A manufacturing district might reduce production. Agricultural lighting might shift temporarily according to what crops can tolerate. Public spaces could use less energy. The systems that preserve immediate life would remain supplied. Redundancy here does not necessarily mean building two complete copies of everything. It means designing enough alternative paths that a single failure does not become a ship-wide failure. The same philosophy would shape whatever primary power technology the vessel carried. Nuclear fission is one possible source because it can produce substantial power without depending on sunlight. Future fusion systems are often discussed for interstellar spacecraft as well. Although controlled fusion power remains an active technological challenge on Earth, and no fusion propulsion system has yet carried a spacecraft, a generation ship belongs far enough beyond present capability that it would be misleading to choose one reactor type and treat it as settled. The useful point is more basic. Its energy supply would need to operate for long periods, use fuel that can realistically be carried or replaced, tolerate maintenance, and remain safe near a population that cannot simply evacuate to another continent. Perhaps the original reactors would not last for the entire voyage. They may not need to. If the ship can manufacture components, process fuel, replace damaged machinery, and commission new power units, then the energy system can be treated as another evolving part of the civilization, rather than one immortal machine. This is the same shift that appeared in life support. Permanent capability matters more than permanent hardware. The first generation may operate equipment designed on Earth. The third may work with machines rebuilt aboard. Later generations could inherit systems whose individual components contain very little original material. And yet the electrical current continues to arrive. Aboard such a vessel, the power plant would probably feel less like a heroic engine room and more like a utility district. People would work there. Students would train there. Maintenance schedules would pass from one year to the next. Certain machines would be opened during planned service periods. Others would remain isolated behind shielding and remote handling systems. The work would become familiar. That familiarity matters because the ship's propulsion system could be very different from its everyday power supply. Moving a city-sized structure between stars demands an amount of energy unlike anything required to keep its lights on. The distinction between those two jobs is easy to overlook. A house needs electrical power. Moving the entire house across a continent requires an entirely different transport system. A generation ship, the same separation on a much larger scale. The energy required to maintain life might be continuous and manageable compared with the energy required to accelerate the vessel itself. Interstellar distances are what make the problem severe. The nearest star system is more than 4 light years away. Even at speeds far beyond those of present spacecraft, crossing such distances can take decades, centuries, or longer. Increasing speed shortens the voyage, but it also increases the energy required to accelerate the ship, and a generation ship would be massive, not only because of its passengers, because of shielding, water, atmosphere, agriculture, manufacturing equipment, reactors, radiators, replacement material, rotating habitats, structural members, and the machinery needed to maintain all of them. Every additional kilogram that makes the world more resilient is another kilogram that propulsion must accelerate. That creates one of the central tensions of the design. A lighter ship is easier to move. A more self-sufficient ship tends to become heavier. The vessel wants reserves because reserves make it safer. Propulsion wants less mass because less mass makes acceleration easier. Shielding asks for material. Engines ask you not to carry it. Habitability asks for space. Structure asks you to support that space. A generation ship exists inside these competing requests. There may never be a perfect balance, only a design whose compromises remain survivable. One possibility is that the ship accelerates gradually, rather than experiencing a brief, dramatic departure followed by an equally dramatic braking maneuver. It might spend long periods gaining speed, coasting, and eventually slowing before arrival. Other concepts imagine propulsion systems that receive energy from outside the spacecraft, reducing how much fuel has to be carried. Still, others rely on enormous onboard stores of reaction mass. Every approach creates a different vessel. The propulsion system influences shielding. Acceleration influences the rotating habitats. Fuel storage influences the distribution of mass. Engine exhaust affects where other structures can safely be placed. Radiators need clear views of space. Cargo routes must avoid sensitive equipment. A ship that once appeared as a cylinder or a ring becomes a collection of connected environments arranged around flows of energy, heat, material, and motion. And somewhere among those environments are the people. For them, most of this might rarely be visible. A family eating breakfast does not need to think about reactor physics each morning. A child walking to a classroom does not need to calculate the thermal load of the agricultural district. Someone reading before sleep does not need to know which radiator panel is carrying away the heat from the lamp beside the bed. That is what functioning infrastructure does. It hides complexity behind reliability. On Earth, entire power stations operate so that a small switch on a wall can feel simple. Inside the moving world, that simplicity would have to be manufactured every day. Perhaps there would be moments when the hidden system became visible. A district lowers its lighting while a power unit is serviced. A corridor closes because engineers are replacing part of a coolant loop. For a few hours, one greenhouse changes its schedule to reduce electrical demand. People adjust. Then the repair is finished. The lights return. The pumps continue. Nothing about the event enters history, and that may be one of the best signs that the ship is working. A civilization does not survive for centuries because nothing ever breaks. It survives because most things that break can become ordinary again. Power would make that possible, but power alone cannot create a replacement bearing, a pressure door, a damaged pipe, a medical instrument, or a new section of structural frame. For the moving world to outlive the machines launched with its first generation, energy must eventually become matter-shaped with purpose. Somewhere aboard, the lights of the workshops would always be on. The workshop at the center of a moving world would have a different relationship with broken things. On Earth, a failed component often disappears into a supply chain. A replacement arrives from a warehouse, another factory makes more, and the deeper industrial system remains mostly invisible to the person performing the repair. Between stars, there is no warehouse beyond the hull. A generation ship would need to carry not only spare parts, but the ability to create parts that nobody thought to store. That ability begins with something humanity has already tested on a much smaller scale. In 2014, an additive manufacturing experiment aboard the International Space Station produced the first object made with a three-dimensional printer in space. Later experiments explored more capable printers and ways to recycle polymer material into feedstock that could be used again. NASA's refabricator demonstration combined recycling and printing in a single system, an early attempt to examine what on-demand manufacturing might mean when replacement hardware cannot simply be delivered from a nearby factory. These experiments do not amount to an orbital industrial base. They are small demonstrations of a much larger idea. If you can carry raw material instead of every possible finished object, the same kilogram of feedstock can have more than one possible future. It might become a pipe fitting this year, a sensor housing decades later, or part of an agricultural pump after being recovered and processed again. That flexibility has value on a voyage where the exact pattern of future failures cannot be known, but a printer alone would not make the ship self-sufficient. A real industrial workshop needs many ways to change matter. Some parts are best built by adding material layer by layer. Others may need cutting, milling, casting, forming, welding, coating, heat treatment, chemical processing, or methods that future engineers develop specifically for long-duration spacecraft. A bearing is not the same manufacturing problem as a water tank. A pressure seal is not the same problem as a structural beam. An optical surface may need precision measured in tiny fractions of a millimeter, while a protective outer panel may tolerate much larger variations. The moving world would therefore carry an industrial vocabulary rather than one universal machine. There would be equipment for making simple objects quickly. Other tools would exist for work that happens rarely but cannot be omitted. And then there would be the machines whose job is to make parts for the other machines. This is where self-sufficiency becomes more demanding. Imagine a milling machine that can produce hundreds of different components. That sounds like a powerful reduction in spare inventory, but the milling machine has motors, bearings, controllers, sensors, cutting tools, lubricants, electrical systems, and surfaces that must remain aligned. Its cutting tools wear, because that is what cutting tools do. Its sensors can drift. Its motors eventually need attention. The machine that reduces the need for spare parts creates a new set of spare parts of its own. So another machine may be able to produce some of them, and another system must inspect what those machines produce. NASA's broader work in space servicing, assembly, and manufacturing treats fabrication as only one part of a larger family of capabilities that also includes inspection, repair, assembly, relocation, and construction. That distinction is useful. Making an object is not enough. A spacecraft also has to know whether the object is good enough to trust. Quality control would be one of the least visible foundations of the ship. A newly manufactured bracket can look perfect and still contain a defect. A seal can have the correct shape and the wrong material properties. A welded joint can appear complete, while a flaw remains inside. On Earth, entire industries exist around metrology, calibration, non-destructive inspection, material testing, and certification. A generation ship would need some version of that world aboard. Measuring instruments would check dimensions. Imaging systems could inspect internal structure. Test samples might be made beside important components to confirm that a manufacturing process is behaving as expected. Critical parts could be tested before anyone allows them near a pressure boundary, rotating structure, or life support loop. And the instruments performing those measurements must themselves remain calibrated. There is an almost circular quality to this problem. You need a reliable instrument to verify a manufactured part. You need reliable standards to verify the instrument. You need people who understand what the measurement means and those standards and skills must remain coherent while decades pass around them. A measurement made in the 5th generation must mean the same thing that it meant when the ship departed. For that reason, the workshop would also be a library, not a library only of books, but of tolerances, material histories, machine settings, test results, failure records, and revisions. A component removed after 40 years might be examined before it is recycled. Where did the crack begin? Was the original material weaker than expected? Did vibration contribute? Did a seal allow moisture into a place where corrosion was not anticipated? The answers could alter how the next version is manufactured. The ship would slowly accumulate an engineering history of itself. This creates a possibility that is easy to miss when generation ships are imagined as monuments. The vessel could become better at maintaining itself. The first pumps may be built according to designs created on Earth. If repeated experience shows that one bearing wears faster than predicted, the onboard engineers could alter the replacement. A pipe connection that is difficult to access could be redesigned when that section is rebuilt. A filter housing might gain a simpler attachment because generations of technicians have learned that the original design takes too long to service. The ship would not remain an untouched artifact from the civilization that launched it. It would be revised. There is something deeply practical about that. No city on Earth remains physically identical for centuries. Pipes are replaced. Buildings change purpose. Roads are widened or removed. Electrical systems that once seemed permanent become obsolete. A generation ship may undergo the same process while the landscape outside remains almost unchanged. One section is renewed while another continues operating. A workshop expands into a neighboring compartment. An old storage area becomes a materials laboratory. A corridor is rerouted because a piece of machinery installed 2 generations earlier needs more service access than anyone predicted. Eventually, very little of the vessel may be original in the ordinary sense. The pattern continues even if the pieces change. That leads to another kind of inventory. A ship cannot manufacture from nothing. Every repaired object has to begin with matter already aboard or acquired somewhere along the route. Metal stock matters, polymers matter, ceramics, glass, carbon-bearing materials, chemical precursors, semiconductor materials, and trace elements can matter in quantities that are small, compared with the hull, but enormous when the nearest external supplier is light years away. Some materials would circulate well. A damaged metal component could be melted, refined, and made into something new, although real recycling always involves energy, equipment, contamination control, and losses. Other materials may be much harder to recover at high purity. Electronics are an especially demanding example. A modern computer is the endpoint of an industrial network involving ultra-pure materials, precise deposition processes, controlled chemistry, microscopic fabrication, sophisticated inspection, and specialized equipment. A generation ship might carry substantial inventories of certain difficult to manufacture components rather than attempting to reproduce every terrestrial industry immediately. Its industrial strategy could have layers, make simple things locally whenever possible, repair complex things before replacing them, design important hardware around reusable modules, carry deep reserves of parts that cannot yet be manufactured aboard, and preserve the capability to expand manufacturing as the voyage continues. NASA's space manufacturing research has pursued this same general advantage at a far smaller scale, reduced dependence on pre-positioned spares by creating, repairing, and eventually recycling hardware closer to where it is needed. The principle is already clear, even though the capability remains limited compared with what a multi-generational vessel would require. For the people aboard, the workshop might become one of the places where generations meet most naturally. An older machinist recognizes a vibration before the monitoring software decides it is unusual. A younger engineer understands a new diagnostic system that did not exist when the machinist was trained. They stand beside the same machine, seeing different parts of the problem. One carries experience, the other carries a newer tool. Neither is sufficient alone. Across enough years, that exchange becomes part of the vessel's continuity. You can imagine shelves containing objects that have been repaired several times. A hand tool whose grip was replaced long ago. A housing with a date etched into its inner surface. A valve design that has reached its 7th revision. They are not relics displayed behind glass. They are still working. The distinction between heritage and equipment becomes less clear on a ship where useful objects may remain inside the community longer than individual lives. Perhaps children occasionally visit the manufacturing district. They watch clean metal stock enter one machine and emerge shaped for a purpose. They see damaged materials sorted into streams for recovery. They learn that the ship is not a collection of things that arrived finished. It is something people continue to make. That lesson may be as important as any technical detail. A generation ship, capable only of consuming its original hardware, would be living on a clock. Every spare used would move it closer to the moment when some critical inventory reached zero. Manufacturing changes the shape of that clock. It does not remove limits, but it allows matter to move between purposes. It allows failed objects to become raw material. It allows experience to become redesign. It allows the population to respond to problems that the first engineers could not predict. And gradually, another realization appears. If the moving world needs an industrial system capable of rebuilding pumps, walls, machines, power equipment, and perhaps entire habitat sections during the voyage, then much of that industrial capability must exist before departure. The ship cannot become a manufacturing civilization only after it leaves. Someone has to build the first workshops. Someone has to supply their raw material. Someone has to assemble structures far larger than anything a single launch vehicle could conveniently carry. Before the moving world can repair itself between the stars, another industrial world may have to learn how to build it in space. The first generation ship may never touch the ground. That possibility follows naturally from everything it has become. A rotating habitat large enough to provide comfortable artificial gravity, wrapped in shielding, filled with water, farms, workshops, power systems, radiators, storage, and industrial equipment would be a poor object to place on top of a rocket. Even if its individual components could survive launch, the completed vessel could grow far beyond the dimensions and masses that present launch vehicles are built to handle. So the ship may begin its existence already in space. Humanity has some experience with that idea. The International Space Station was not launched as one finished structure. Its major components has arrived separately over many missions and were connected in orbit. Modules, trusses, solar arrays, laboratories, radiators, and other systems gradually became a single operating complex. That achievement proved something important. Large structures do not always need to fit inside one rocket. But a generation ship would push the lesson much farther. The station was assembled largely from finished components manufactured and tested on Earth. Orbit was the place where those components were connected. A ship larger than a city could eventually require orbit to become the place where material is shaped as well. That is a different kind of activity. Imagine a construction site where the building never rests on the ground. There is no foundation beneath it. Every unfinished section has to be controlled because an unsecured object does not fall harmlessly to the floor. It keeps moving. Large pieces approaching one another carry momentum. Cargo arriving from another orbit must match the construction site's trajectory before it can be transferred. Structural sections need to be positioned and held while connections are made. Welding, fastening, inspection, pressure testing, electrical integration, and countless smaller jobs have to happen while the entire site continues traveling around a planet or through some other chosen orbit. The shipyard itself becomes a spacecraft. It needs power. It needs navigation. It needs communications. It needs thermal control. It needs storage for material waiting to be used. It needs machinery for moving loads between work areas. And it needs somewhere to put unfinished sections that may remain incomplete for months or years. That last requirement changes the rhythm of construction. On Earth, a factory can receive steel plate by truck in the morning and send a finished component through another door later in the day. An orbital yard may receive material through a transport system stretching across thousands or millions of kilometers. A delayed shipment is not a truck arriving after lunch. It may be a cargo vehicle missing a transfer window and reaching the site much later than planned. For construction to become routine, the yard would need buffers, storage depots, reserve feedstock, spare machinery, extra power capacity, tugs capable of rearranging cargo when schedules change. The visible ship under construction would be only one part of a much larger network. At first, most of its material might still rise from Earth. That would place a severe burden on launch systems. Every kilogram carried from the surface must climb through Earth's gravitational field before it can become part of the vessel. Rockets can perform that task, but a generation ship could require such large quantity of structural and protective mass that transporting all of it from Earth becomes less attractive as the design grows, and much of that mass may be very ordinary. Radiation shielding does not care whether its atoms were polished in a terrestrial factory. A protective layer may need bulk material more than delicate craftsmanship. Water intended for storage and shielding remains water whether it came from Earth, the Moon, or a suitable asteroid. Structural metals may eventually be processed far from the surface where the first shipyards were imagined. That leads toward one of the most important changes in the construction problem. Perhaps Earth does not need to provide all the mass. The Moon contains abundant mineral material. Some permanently shadowed regions near its poles contain water ice. Asteroids contain mixtures of rock, metals, carbon-bearing compounds, and, in some cases, water-rich minerals. Humanity has not established industrial mining on any of these bodies. Present missions are still operating at the level of exploration, sampling, prospecting, and small technological demonstrations. So an off-world supply chain for generation ships belongs to a possible future, not to current industrial reality. But the reason it is considered is straightforward. If large quantities of material are already outside Earth's deep gravitational well, future industry may find value in processing that material closer to where it will be used. The first useful product may not look like a spacecraft component. It could be water. Water can support people. It can be separated into hydrogen and oxygen when an energy system and appropriate equipment are available. Those elements can have uses in propulsion and life support. Stored water can also contribute to radiation protection. One resource can therefore enter several parts of the industrial network. Lunar material could provide other possibilities. Minerals contain oxygen bound chemically within them. Metals and glass, like materials, might eventually be extracted or processed for construction. Even relatively unrefined material could have value when enormous quantities of shielding are required. Asteroids present a different opportunity. Their weak gravity means material may be moved away from some small bodies with less energy than would be required to lift the same mass from Earth. But that does not make asteroid mining simple. A small body offers very little gravity to hold machinery against its surface. Material can escape. Dust can behave in unfamiliar ways. A mining system may need anchors or other methods of controlling reaction forces. Processing equipment must work without the industrial support available on Earth. And once material has been collected, it still has to reach the shipyard. Extraction is only the first link. Imagine a chunk of water-rich asteroid material becoming part of the ship's shielding decades later. Before that happens, a prospecting mission identifies a useful body. Mining equipment reaches it, material is collected. A processing system separates what is useful. The water or refined product enters storage. A cargo vehicle moves that material onto another trajectory. A depot receives it. Eventually, a tug delivers it to the construction site. Only then can the shipyard decide where those atoms belong. This is why building the moving world may require an economy before it requires the ship. Mining without transport produces stranded resources. Transport without storage produces scheduling problems. Storage without power creates tanks and equipment that cannot maintain themselves. Refining without maintenance becomes a temporary experiment. The separate capabilities have to become dependable enough that other systems can trust them. Trust is a useful measure of industrial maturity. A construction manager on Earth does not celebrate every time steel arrives. The arrival is expected. The project was scheduled around it. A future orbital shipyard reaches the same threshold when a shipment of water, metal, or structural feedstock becomes ordinary enough to appear on a calendar rather than in a history book. Perhaps that industrial network begins near Earth. Perhaps lunar resources make cislunar space more important. Perhaps asteroid materials eventually shift the center of activity farther outward. No one can know the final map yet. The best location for a shipyard would depend on where resources become available, how propulsion develops, how much energy different transport routes require, where people can live safely, and where the completed ship is intended to go. But one principle is likely to remain useful. Move the smallest amount of heavy material the shortest practical distance. If millions of tons of shielding come from the moon or asteroids, bringing all of that mass down toward Earth, only to send it outward again, may make less sense than building closer to the supply routes themselves. Earth could still provide what it does best: people, specialized electronics, medical equipment, complex instruments, high-value components that remain difficult to manufacture elsewhere. The bulk material might arrive from another direction. The construction site becomes the place where several streams meet. One stream carries precision hardware outward from Earth. Another carries water from a storage depot. Another brings processed metal. Tugs move unfinished sections between assembly areas. Robotic systems inspect long structural members. Manufacturing equipment produces pieces too large to fit inside any launch fairing. The generation ship grows without ever having been contained inside a single vehicle. At first, there may not even be anything recognizable as a ship. A power station appears. Storage follows. A construction truss is extended. Manufacturing bays begin operating. Radiators unfold. Crew quarters or robotic maintenance facilities arrive. For years, the site may resemble an industrial district with no obvious destination. Then, large structural elements begin joining one another. A rotating habitat ring takes shape. Shielding sections surround it. Another habitat follows. Power and thermal systems spread along the central structure. The object slowly acquires a geometry that could be recognized from a distance. Even then, departure may still be years away. Every pressure region has to be tested. Every major system must operate under realistic loads. The life support network needs time to reveal weaknesses. Agricultural systems need repeated cycles. Rotating structures need inspection after long periods of motion. manufacturing systems must demonstrate that they can support not only construction but future maintenance. The vessel would have to become a working world before anyone trusts it to leave the industrial network that created it. That period might be one of the most important parts of the entire project. People could live aboard while supplies are still nearby. Children might even be born during commissioning if the testing phase became long enough, though any real decision of that kind would involve biological, medical, and ethical questions far beyond engineering alone. The population would learn the ship. While the ship remained within reach of help, failures would become lessons, while replacement hardware could still arrive. Designs could change. Systems that looked elegant on paper might be rebuilt after years of daily use. By departure, the moving world would already have a history. Its oldest corridors might carry signs of repairs. One greenhouse could belong to a newer than the others, a structural section. Before the journey even began, there would be people aboard who remembered when the ship was still attached to construction frames, and eventually those frames would begin to move away. Tugs would clear the working area. The last major cargo would be stored. The surrounding industrial traffic would thin. For the first time, the vessel would contain nearly everything its population expects to need without a nearby warehouse, factory, or rescue vehicle. The shipyard would remain behind. Ahead would be a journey, measured not in missions but in lives. And the final test would no longer belong to the machines that built the world. It would belong to the society asked to continue inside it. A ship can be designed to carry water for centuries. It is much harder to design a society for the same length of time. Machines fail in ways engineers can sometimes predict. Bearings wear, filters clog, radiation damages materials, pumps accumulate operating hours. Human communities change for reasons that cannot be reduced to maintenance schedules. A generation ship would have to carry both. The first crew might leave with a clear understanding of the mission. They would remember Earth directly. They would know why the vessel was built, why its destination was chosen, and what generations of engineers had hoped to accomplish. Their children would inherit that purpose. Their grandchildren might inherit mostly the explanation. Several generations later, the journey could feel less like an expedition and more like the natural condition of existence. That difference matters. For the people born aboard, Earth would not be home in the ordinary sense. It would be a place described through recordings, archives, family histories, scientific databases, art, languages, and images of landscapes their bodies had never experienced. They might know what an ocean looks like long before they have ever stood beside one. They could understand, intellectually, that a natural horizon continues beyond anything visible, even though every horizon they know curves upward into the architecture of the ship. Rain might be something studied before it is ever felt. A forest could be familiar as biology and unfamiliar as scale. The mission would therefore have to survive a transformation. It begins as a decision made by people on Earth. It continues as a life inherited by people who had no part in that decision. There is no engineering formula that settles what obligations this creates. Questions of consent, governance, reproductive freedom, education, cultural continuity, and individual choice would become central to any serious generation ship proposal. They cannot simply be added after the propulsion system is designed. The human structure is part of the vessel. Even population size would involve more than finding enough beds. A multi-generational community would need enough people to remain biologically healthy, socially resilient, and capable of sustaining the wide range of skills required by the ship. Researchers have modeled population genetics for isolated space settlements, but proposed minimum populations vary widely depending on assumptions about voyage length, reproductive patterns, stored genetic material, medical technology, population management, and the degree of risk considered acceptable. So there is no single trustworthy number that can be written on the hull and called sufficient. A real design would need margins. It might carry a population larger than the theoretical minimum. It could preserve reproductive cells or other genetic material in protected storage. Medical systems might monitor genetic risks across generations, but biological diversity would be only one kind of diversity the ship needs. A settlement filled entirely with excellent engineers would still be incomplete. Someone must teach children. Someone must care for people who are sick. Someone must understand food systems, ecology, materials, software, power networks, conflict resolution, sanitation, and mental health. Someone must preserve history. Someone must make music, stories, games, ceremonies, and places people about enough to maintain. A city is not merely a collection of technical professions. The moving world would discover this early. You can imagine a school, somewhere within one rotating district. Children learn mathematics because the ship needs engineers, but also because mathematics belongs to their intellectual inheritance. They study the biology of crops growing only a few corridors away. They learn the geometry of the habitat beneath their feet. Perhaps one lesson explains why apparent gravity weakens toward the axis. Another covers the star system their descendants may eventually enter. Then the lesson ends, and the children leave to do something that has nothing to do with the mission. They play. That ordinary moment may be as important as the technical curriculum. A society organized entirely around survival could become difficult to inhabit. People need portions of life that are not justified by engineering. A room can exist because people enjoy gathering there. A garden can contain plants that contribute little to food production. A wall can hold paintings instead of equipment. A holiday can commemorate something that no longer improves the ship's efficiency. This is not wasted mass in the same simple sense that an unnecessary component might be. Culture is one of the systems that makes a human environment sustainable. Its design cannot be fully planned before departure. The first generation could establish institutions, traditions, and laws, but later inhabitants would interpret and change them. Words would shift. Music would change. New customs could appear around events unique to the ship. Perhaps certain maintenance cycles become markers in the calendar. Perhaps the passing of a navigational milestone is remembered each year. Perhaps children grow up with stories about sections of the vessel that were rebuilt long before they were born. A civilization separated from Earth would gradually become its own civilization. That makes governance unusually important. A short spacecraft mission can operate with a clear command structure because the crew agreed to participate. The mission has a limited duration and an extensive organization on Earth remains involved. A generation ship cannot assume those conditions forever. Someone born a century into the voyage did not volunteer for a mission in the normal sense. The destination may remain decades away. Returning to Earth may be physically impossible. Authority, therefore, needs legitimacy that can survive beyond the original mission plan. There are many possible political arrangements, and none can be selected confidently from physics alone. The ship might use representative institutions. Some responsibilities may belong to professional technical organizations. Certain emergency powers could exist for immediate hazards, while broader decisions remain civilian. Rules might be revisable under procedures designed before departure and modified later. Whatever system develops, it would need to manage a difficult balance. Some parts of the vessel cannot be governed by preference. Atmospheric chemistry does not change after a vote. A pressure limit remains a pressure limit. The rotational structure cannot safely operate outside certain conditions because a majority would prefer otherwise. Technical reality creates boundaries. Inside those boundaries, human beings still need meaningful choices. Where to work, whom to live with, what to believe, what to study, how to spend a lifetime that happens to occur inside an interstellar machine. One of the most delicate questions concerns the destination itself. The founders might see arrival as the entire purpose of the project. Later generations could think differently. If the ship is functional, if its inhabitants have known no other home, and if the destination presents uncertainties the founders did not anticipate, should arrival remain mandatory? A settlement capable of sustaining itself between stars may eventually possess options its designers never expected. It could alter plans, delay a maneuver, change how the destination is approached. Perhaps observations made during the voyage reveal that the target system is less suitable than early astronomers believed. Perhaps another destination becomes preferable. Perhaps the society aboard wants to remain partly space-based rather than descend immediately to a planetary surface. These possibilities are speculative, but the principle behind them is practical. A voyage lasting generations must allow future people to respond to new information. The founders cannot make every decision for descendants they will never meet. This is another reason preserving scientific understanding matters. An archive should not merely tell future inhabitants what to do. It should help them understand why. Design assumptions need to remain visible. Models should be revisable. Old decisions should carry their evidence with them. A rule whose reasoning has been forgotten can become either fragile or unnecessarily rigid. A society capable of questioning inherited plans may actually be better equipped to preserve the vessel than one trained only to obey them. Across the centuries, there would still be moments of continuity. A technician might open a maintenance record written by someone 7 generations earlier. The language would be familiar, though perhaps slightly old-fashioned. The damaged valve described there no longer exists. The original pump model was replaced long ago, but the person who wrote the note had noticed a pattern in the coolant system that remains useful. For a few minutes, 2 people separated by centuries are working on the same problem. That is what inheritance can look like inside the ship. Not an untouched tradition, a conversation that continues because someone left enough understanding behind for another person to answer. Eventually, the destination star would stop being an abstract point in a navigation system. Its light would grow brighter. Observatories aboard the vessel would measure its planets with greater precision than was possible when the journey began. The population might receive images of worlds no human being had ever seen so closely. Students who had spent their lives studying old projections could compare them with new measurements, arriving from instruments only a short distance away. By astronomical standards, then the society would face its final transition. For generations, survival meant keeping the moving world intact. Soon, survival might require learning how to leave it. The ship that had been everything would become one place among others. And before anyone opened the first route toward that unfamiliar world, the people aboard would have to decide what parts of their moving home were meant to travel with them. There is a moment in almost every imagined interstellar voyage when attention shifts toward arrival. The destination star grows brighter. Instruments begin resolving worlds that once existed only as points in data. Navigation becomes more precise. The long crossing finally seems to have an edge, but for the people living aboard a generation ship, arrival would not erase the world that carried them there. By then, the vessel could be centuries old. Its walls may have been repaired many times. Entire systems may have been replaced. Farms may contain crop varieties selected aboard. Workshops may use tools designed by engineers who never saw Earth. The language spoken in one neighborhood may carry expressions that did not exist when the ship departed. What began as a spacecraft would have become history, infrastructure, and home. That makes arrival less like stepping off a train and more like asking a city to decide what it will become next. Even before reaching the destination, the ship would begin studying it with increasing detail. A star that appeared from Earth as a remote point would slowly become a physical environment. Its light would reveal activity. Its planets would move against the background. Their masses, atmospheres, temperatures, magnetic environments, and orbital conditions could be measured with instruments much closer than any telescope left behind. Some expectations might be confirmed. Others might not survive the journey. A world believed promising at departure could prove hostile. Another, once overlooked, might become more interesting. Moons could matter. Asteroids could matter. Orbital space around the new star could matter more than any planetary surface. The generation ship would arrive, carrying something its founders could never possess. Local knowledge. That knowledge could change the meaning of the mission. A destination selected centuries earlier was selected with centuries earlier information. The people making the final decisions would have a responsibility that the original planners could not take from them. They would need to decide where to go now. Perhaps the vessel enters a wide orbit and spends years surveying the system. Perhaps smaller robotic craft leave first. They map surfaces, sample atmospheres, measure radiation, search for useful materials, study anything that might affect human settlement. No sensible community that had survived an interstellar crossing would need to rush the final few million kilometers. The ship itself would already support life. Time, for once, could be used carefully. There is a symmetry in that. For generations, the population survived because it resisted the idea that any one system should be trusted without inspection. Water was measured, structures were checked, machines were tested, agriculture was watched. Repairs were made before failures spread. Arrival would ask for the same habit on a larger scale. Do not assume the new world is safe because it is beautiful. Measure it, understand it. Approach it in stages. The first human beings to leave the ship might not walk onto a planetary surface at all. They might enter another habitat built from material gathered in the new system. They could work at an orbital station. They might help construct a settlement on a moon. A rotating habitat could remain preferable in a system where no nearby planet offers an environment suitable for unprotected human life. The destination does not have to resemble Earth for the journey to have meaning. A civilization that learned to live between stars would already know how to inhabit places where nature does not provide everything the body requires. That may be one of the deepest transformations hidden inside the generation ship idea. At the beginning, the ship seems to be a temporary answer to distance. Build a closed world because the stars are too far apart. Cross the gap, reach another planet, then leave the machine behind. But a successful generation ship would prove something larger. It would prove that a human community could carry many of the conditions of life with it. Not perfectly, not independently of physics, not without materials, energy, maintenance, and limits, but with enough control over air, water, food production, manufacturing, knowledge, and habitat that a planet would no longer be the only conceivable place where a society could continue. The ship might therefore remain inhabited after arrival. Some people may choose to leave, others may stay. Children could grow up while new settlements are being built elsewhere in the system. Cargo would begin moving in both directions. Material collected locally could enter the old workshops. New structures could be attached. The vessel that once crossed empty interstellar distance could become the oldest district of a new network of habitats. Its engines might never perform another interstellar departure, Its rotating neighborhoods could continue turning. A place designed for travel could become a place people simply live. And for those people, the history of Earth would remain present in unusual ways. They would carry the biological history of a planet 4 light years away, or 10, or 20. Their bodies would still contain the consequences of gravity, sunlight, oceans, atmosphere, and evolution on a world most of them had never seen. Plants in the agricultural sections would carry another part of that inheritance. Seeds would open under artificial lamps. Roots would move through engineered growing systems. Leaves would exchange gases with an atmosphere maintained by machines. Yet their chemistry would remain part of the same story that began beneath a natural sun. The distance would not break that continuity. It would make the continuity more visible. Perhaps an archive aboard the ship contains recordings from before departure. There are oceans, wind moving through trees, city streets, voices of engineers describing components that no longer exist. Photographs of the construction yard before the first habitat began turning. The people watching these images may recognize the names of their ancestors. They may also notice how unfamiliar the ship looks in its earliest form. The vessel they know has changed. Walls have moved, equipment has been replaced, new districts have been added. Even the oldest surviving structures carry repairs that tell their own chronology. The ship reached another star not by remaining unchanged, but by preserving the ability to change without losing what mattered. That may be the central engineering lesson of the moving world. Durability does not mean making every object permanent. It means making renewal possible. The life support system survives because it can be serviced. The workshop survives because its tools can be rebuilt. Knowledge survives because it can be taught. A community survives because later generations are allowed to understand, question, repair, and reshape what they inherit. No single machine crosses the centuries untouched. The continuity belongs to the system. That perspective also brings the enormous scale of the project back into view. Before such a vessel could exist, humanity would need ability far beyond the ones available today. Large-scale construction in space, deep resource recycling, reliable closed or nearly closed life support, long-duration artificial gravity habitats, extensive manufacturing away from Earth, energy systems capable of operating for very long periods, radiation protection, medical knowledge for generations living beyond a planetary environment, and an industrial network capable of creating something whose mass might eventually be measured more like infrastructure than spacecraft. None of those requirements disappears because the idea is compelling. A generation ship remains speculative. Its feasibility has not been demonstrated. Some problems may prove harder than present concepts suggest. Others may be solved in ways that would look unfamiliar to engineers today. The value of thinking about such a ship does not depend on pretending we already know how to build one. The idea is useful because it forces familiar technologies to continue farther than they usually do. A water recycler is no longer judged after a mission. It is judged after generations. A habitat is no longer somewhere people tolerate for a year. It is where someone spends an entire childhood. A workshop is no longer backup equipment. It becomes part of the economy. A spacecraft is no longer a vehicle surrounded by civilization. It has to carry enough civilization with it to remain functional when everything else is far behind. And once the question is framed that way, the city-sized hull is no longer the most difficult part to imagine. The difficult part is everything that has to continue inside it. The air moving tonight and still moving a century later, the water passing from one person to another through machines, plants, tanks, and time. The skills passed from teacher to student. The repair record opened by someone whose grandparents had not yet been born when the first note was written. The small decisions that prevent a large system from slowly coming apart. Generation ship would cross interstellar space through millions of such ordinary acts. Not one endless heroic moment, a sequence of mornings, work shifts, meals, repairs, lessons, harvests, birthdays, inspections, arguments resolved, parts replaced. Children growing older beneath a sky built inside a rotating structure. Outside, the stars would change position almost imperceptibly. The sun would become another bright point behind them. The destination would spend decades becoming brighter ahead. And through all of it, the world would continue turning around its own axis, holding its atmosphere against its floor, carrying its stored water in the walls, releasing heat into the space beyond, and giving the people inside a direction they could cool down. Eventually, perhaps, another star would fill the windows. By then, the people looking toward it would not be passengers from Earth. They would be inhabitants of the moving world, and their oldest home would still be turning beneath their feet.